Welcome to the deep dive. Ever just look up at the sun and wonder, how does it do that? How does it keep burning, well, not really burning, but shining for billions of years?
It's an amazing question, isn't it? And the answer isn't fire, it's nuclear reactions deep inside its core.
Exactly. And that same basic science, nuclear chemistry,
Mm.
the study of changes inside the atom's nucleus, it actually touches our lives in, well, in ways you might not even realize.
Absolutely. From figuring out how old ancient artifacts are to medical scans, even, how smoke detectors work, it's everywhere.
It really is. So today, we're diving deep into this fascinating world. We're using a key chapter from the textbook Chemistry, the Central Science, as our guide.
A solid foundation for this topic.
Our mission here is to take those core chemical principles and break them down, make them clear, engaging, maybe even a bit fun. We want to show you the real-world connections, the history, and how it all fits together. So let's unpack this.
Okay, so at its most basic level, nuclear chemistry is all about reactions that change the atomic nucleus. This is totally different from regular chemistry, which just involves the electrons around the nucleus.
Right. In nuclear reactions, elements can actually change into completely different elements. That's kind of the big deal, isn't it?
That's the core of it, yeah.
So let's quickly recap the nucleus itself. We've got protons, those are positive, and neutrons, which are neutral. Stick them together, and scientists call them nucleons.
Uh-huh. And the number of protons, that's the atomic number. It tells you what element you've got. Hydrogen always has one, helium always has two, and so on.
But the number of neutrons can vary, right? That gives you the mass number, protons plus neutrons, and those variations of the same element are called isotopes.
Exactly. Like uranium. All uranium atoms have 92 protons, but you can have uranium-235 or uranium-238, which just means they have different numbers of neutrons.
Not equally common or stable either.
Not at all. Uranium-238 makes up over 99% of the uranium on Earth, while U-235 is much rarer. And their stability is different, too. Any specific combo of protons and neutrons is called a nuclide.
Okay, nuclide. And if it's unstable?
Then we call it a radionuclide. And the atoms themselves are radioisotopes. Unstable means they're going to spontaneously change or decay.
So what does decay actually mean here? What's happening inside that unstable nucleus?
It means the nucleus is spontaneously spitting out particles or energy or both. It's called radioactive decay. It's basically the nucleus trying to get to a more stable, lower energy state.
And there are a few main ways it does this, the big three types of radiation.
Yeah, that's a good way to put it. First up is alpha decay. The nucleus kicks out an alpha particle.
Which is?
Essentially, it's a helium-4 nucleus, so 2 protons and 2 neutrons bundled together. When, say, uranium-238 does this, it loses those 2 protons and 2 neutrons, and boom, it becomes thorium-234.
Ah, so the atomic number goes down by 2, and the mass number goes down by 4. It changes the element.
Precisely. And you have to make sure those numbers balance on both sides of the nuclear equation. Mass numbers have to balance, and atomic numbers have to balance. That's crucial.
Got it. Okay, what's next after alpha?
Then you have beta decay. This one's a bit different. The nucleus emits a high-speed electron.
An electron. But I thought the nucleus only had protons and neutrons.
Good point. What's effectively happening is a neutron inside the nucleus is transforming into a proton, and it emits an electron in the process. So take iodine-131. It undergoes beta decay and becomes xenon-131.
So the mass number stays the same, but the atomic number goes up by 1 because it gained a proton.
Exactly right. Iodine becomes xenon.
Okay. Alpha, beta. What's the third?
Gamma radiation. This isn't particles. It's pure energy, high-energy photons.
Yep.
Gamma emission usually happens alongside alpha or beta decay as the nucleus settles down into a lower energy state after the main event. It doesn't change the element or the mass number. It just sheds excess energy.
Are there other types of decay besides these three?
Oh, yes. 2 other key ones are positron emission, where a proton turns into a neutron and emits a positively charged electron, a positron, like carbon-11 turning into boron-11.
Ah, a positive electron. Okay.
And then there's electron capture, where the nucleus actually grabs one of its own inner orbital electrons, combines it with a proton, and turns it into a neutron, rubidium-81 becoming krypton-81 as an example.
It's amazing that these tiny, spontaneous changes are things we actually harness, like you said, for medicine. Cobalt-60's gamma rays for cancer, or PET scans using positron emission.
It really bridges fundamental science and practical application.
Which brings up a big question. Why? Why are some nuclei unstable in the first place? What makes them decay?
Ah, that's the million-dollar question. It boils down to the forces inside the nucleus. You've got protons all positively charged packed together. They should repel each other massively, right?
Yeah, electromagnetism says they should fly apart.
But they don't because of the strong nuclear force. It's an incredibly powerful but very short-range attractive force that acts between all nucleons, protons, and neutrons. Neutrons are key here. They provide extra glue without adding more repulsion.
So it's about finding the right balance, like the right ratio of neutrons to protons.
Exactly. The neutron to proton ratio, NP, is probably the single best indicator of stability. For light elements, stable nuclei tend to have a ratio close to 1.1, one neutron for every proton.
But that changes for heavier elements.
It does. As you get more protons crammed in, you need proportionally more neutrons to overcome that increasing repulsion. So for heavier stable nuclei, the NP ratio climbs maybe up to 1.5.1 or even higher.
And if a nucleus doesn't have the right ratio, it's unstable. Is that where this belt of stability idea comes in?
That's it. You can plot all known nuclides on a graph of neutrons versus protons. The stable ones form a sort of narrow band, or belt. Nuclei that fall outside this belt are radioactive. They'll decay in ways that move them closer to the belt.
Okay, so if a nucleus is, say, above the belt, too many neutrons.
It'll likely undergo beta decay. Remember, beta decay turns a neutron into a proton, so it decreases the N-key ratio, moving it down towards the belt.
And if it's below the belt, too many protons, not enough neutrons.
Then it's likely to undergo positron emission or electron capture. Both of those processes turn a proton into a neutron, increasing the NP ratio and moving it up towards the belt.
What about the really heavy elements? You mentioned uranium earlier.
Right. Once you get to element 84, polonium, and beyond, all known isotopes are radioactive regardless of their NP ratio. They're just too big to be truly stable. These heavyweights often undergo alpha decay, which sheds both protons and neutrons, making the nucleus smaller.
And sometimes it takes more than one decay step to get stable, like a cascade.
Yes, absolutely. Those are radioactive decay chains or series. Uranium-238, for example, goes through, I think it's 14 decay steps, a mix of alpha and beta decays over billions of years before it finally ends up as stable lead-206.
Wow. Are there other clues to stability besides just the NP ratio?
Yeah, a couple interesting patterns. Nuclei with certain specific numbers of protons or neutrons, 2, 8, 20, 20, 50, 82, and 126 for neutrons, seem to be unusually stable. They're called magic numbers. It's kind of analogous to filled electron shells in atoms.
Yeah, magic numbers. Okay.
And there's also a general observation that nuclei with even numbers of protons and neutrons tend to be more stable than those with odd numbers of both.
Interesting patterns. Okay, so that's spontaneous decay. But you mentioned we can also make nuclei change, force them to transform.
We can indeed. It's called nuclear transmutation, literally changing one element into another artificially.
Wasn't that like the alchemist's dream?
Sort of. But the first person to actually achieve it scientifically was Ernest Rutherford back in 1919. He bombarded nitrogen gas with alpha particles and detected oxygen-17 being formed. First artificial transmutation. Huge deal.
How do scientists do that today? You can't just throw alpha particles at stuff, can you?
Well, sometimes you can, but often you need more energy. You need ways to accelerate particles to smash into the target nuclei with enough force. That's where particle accelerators come in machines like cyclotrons or synchrotrons, sometimes called atom smashers.
Right. They whip charged particles around really fast to give them energy.
Exactly. To overcome the electrostatic repulsion between the incoming positive particle and the positive nucleus.
But what if you use neutrons? They don't have a charge.
Excellent point. Neutrons are fantastic projectiles for transmutation because they aren't repelled by the nucleus. They can just wander right in, even at low energies. That's how we make isotopes like cobalt-60 for cancer therapy, by bombarding stable cobalt-59 with neutrons in a reactor.
And this has let us create elements that don't even exist naturally, heavier than uranium.
That's right, the transuranium elements. Starting with neptunium and plutonium, which were made by hitting uranium-238 with neutrons, we've now synthesized elements all the way up to, I think oganesson, element 118, is the current heaviest confirmed one.
How do they even make those super heavy ones?
It involves smashing heavy nuclei together in those accelerators, like element 112, copernicium, was made by fusing lead and zinc atoms. It's incredibly difficult. Often they only create a few atoms that decay almost instantly. Confirming their existence is a massive challenge. IUPAC, the International Union for Pure and Applied Chemistry, oversees the verification and naming.
Incredible. Okay, so we know nuclei decay, and we know why some decay, and that we can even force them to change. Let's talk about the timing. Here's where it gets really interesting. The idea of a nuclear clock.
Ah, yes, half-life. This is a cornerstone concept. Every radioisotope decays at a specific predictable rate. The half-life is the time it takes for exactly half of the radioactive atoms in a sample to decay.
And this rate is constant, like nothing affects it.
Pretty much nothing practical. Temperature, pressure, whether it's chemically bonded to something else, none of that changes the nuclear decay rate or the half-life. It's purely a property of that specific nuclide.
And that's what lets us use it for dating things. Radiometric dating.
Precisely. Because the clock ticks so reliably, the most famous example is probably radiocarbon dating, using carbon-14.
How does that one work?
Okay, so high-energy cosmic rays hit the upper atmosphere, constantly creating carbon-14 from nitrogen. This C14 gets incorporated into carbon dioxide. Plants breathe it in, animals eat the plants. So as long as something is alive, it's taking in C14 and maintaining a roughly constant ratio of C14 to stable C12, matching the atmosphere.
But when it dies?
Intake stops. The C14 clock starts ticking. It decays via beta emission with a half-life of about 5,700 years. So by measuring the remaining C14-C12 ratio in a sample like wood, bone, cloth, scientists can figure out how long ago the organism died.
How far back can carbon dating go?
It's really useful, but it has limits. After about 50,000 years or so, maybe 9 half-lives, there's just too little C14 left to measure accurately. And scientists have to carefully account for past fluctuations in atmospheric C14 levels using things like tree ring data.
So for really ancient stuff like rocks or the Earth itself, C14 won't work. What then?
Then we use isotopes with much, much longer half-lives, like uranium-lead dating. Uranium-238 has a half-life of 4.5 billion years. It decays through that long chain we mentioned, eventually ending up as stable lead-206.
So you measure the ratio of the lead daughter to the remaining uranium parent in a rock.
Exactly. That ratio tells you how long the clock has been running since the rock solidified. That's how we've estimated the age of the Earth, somewhere around 4 to 4.5 billion years old, based on the oldest rocks and meteorites.
Amazing. So how do we actually measure or quantify this radioactivity? You hear units like becquerel or curie.
Right. The becquerel BQ is the standard SI unit. It's super simple. 1 BQ is just 1 nuclear disintegration per second.
Okay, that seems straightforward.
It is, but it's often a very small number for practical samples. The older unit, the curie, CI, is much larger. 1 curie is 3.7 times 10 to the 10th disintegrations per second. That's a huge number. It was originally based on the activity of 1 gram of radium.
Wow. And how do we even detect this stuff? It's invisible. Didn't Becquerel discover it by accident?
He did. He left some uranium salt on a photographic plate in a drawer and found the plate got fogged, even in the dark. That basic principle is still used in film badges worn by radiation workers. The more radiation, the darker the film gets.
But we have more sophisticated detectors now, right? Like that clicking Geiger counter sound everyone knows.
Absolutely. A Geiger counter works by having radiation ionize a gas inside a tube. Each ionization event creates a little pulse of electricity, which can be counted, hence the clicks.
Are there other kinds?
Yes, scintillation counters are often more sensitive. They use materials called phosphors that emit a tiny flash of light, a scintillation, when radiation hits them. Electronic detectors then pick up those light flashes and count them.
Okay, so we can detect it very precisely, and that leads to another clever application. Radio tracers.
Yeah, these are really neat. The key idea is that different isotopes of the same element behave almost identically in chemical reactions. So you can add a tiny amount of a radioactive isotope to a larger amount of the stable isotope, and then follow where the radioactivity goes. It traces the path of the element.
Like putting a tiny radio beacon on some atoms.
That's a great analogy. Scientists used carbon-14 this way to figure out the path of carbon during photosynthesis, how CO2 actually gets turned into glucose. And oxygen-18 helps show that the oxygen plants release comes from water, not CO2.
And this is huge in medicine too, isn't it?
Immense. Doctors use radio tracers routinely. Iodine-131 to check thyroid function, iron-59 to study red blood cells. Technetium-99 meters is incredibly versatile for imaging the heart, bones, liver, lungs. Lots of things.
You mentioned PET scans earlier too. How do those work again? They use positrons.
Right, positron emission tomography. You inject a compound, often a modified sugar molecule, tagged with a positron-emitting isotope like fluorine-18. This compound goes to areas of high metabolic activity like active brain regions or tumors.
And the positron.
When the nucleus emits a positron, it almost immediately bumps into an electron nearby in the tissue. They annihilate each other.
Annihilate, like disappear.
Yep. Their mass is converted into pure energy, specifically into two gamma rays that fly off in exactly opposite directions. A ring of detectors around the patient picks up these pairs of gamma rays.
And because they fly off opposite each other, the computer can pinpoint exactly where the annihilation happened.
Precisely. By tracking thousands of these events, the computer builds up a 3D map showing where the tracer concentrated. It lets the doctors literally see metabolic processes happening, like how the brain is using glucose, which is invaluable for diagnosing things like Alzheimer's or cancer.
Incredible. And you even find this stuff in smoke detectors.
Some types, yeah. Ionization smoke detectors use a tiny amount of americium-241, an alpha emitter, to ionize the air in a small chamber. Smoke particles disrupt that ionization, triggering the alarm.
Wow. Okay, from the tiniest tracers to, well, the biggest energies imaginable. Let's talk about the sheer power locked in the nucleus. And that has to start with EMC-Washi, right?
It really does. Einstein's equation is the key. It tells us mass and energy are two forms of the same thing, and they can be converted into each other. And that c squared, the speed of light squared, is a massive number.
Meaning even a tiny, tiny change in mass equals a gigantic amount of energy.
Exactly. In chemical reactions, the mass changes are practically zero, undetectable. But in nuclear reactions, a small but measurable amount of mass is converted into energy, and the energy release is enormous, millions of times greater than chemical reactions.
Where does that mass difference actually come from in a nucleus? You hear about mass defect.
Right. If you take a nucleus like helium-4 and weigh it very precisely, and then you weigh its components separately, 2 protons and 2 neutrons, you'll find the helium nucleus weighs less than the sum of its parts.
Huh. So mass disappears when they bind together.
It's converted into energy, the energy released when the nucleus formed. That difference in mass is the mass defect. And the energy equivalent of that mass defect is called the nuclear binding energy. It's the energy you'd need to put back in to break the nucleus apart again.
So more binding energy means a more stable nucleus.
Generally, yes. If you plot the binding energy per nucleon against the mass number, you see a curve. It peaks around iron 56. Nuclei around iron are the most tightly bound, the most stable.
And that explains both fission and fusion, because elements want to get closer to that iron peak.
You've got it. Heavy nuclei, way past iron, like uranium, are less stable than medium-sized nuclei. So they can release energy by splitting apart into smaller pieces. That's fission.
And really light nuclei, like hydrogen isotopes.
They're also less stable than things like helium or carbon, so they can release even more energy by fusing together to form heavier nuclei. That's fusion. Both processes move towards that stability peak around iron.
Let's tackle fission first. Splitting the atom, how does that work?
Fission usually involves hitting a heavy nucleus like uranium-235 or plutonium-239 with a neutron, especially a slow-moving one. The nucleus absorbs the neutron, becomes unstable, and splits into 2 smaller nuclei, releasing a huge amount of energy and, crucially, 2 or 3 more neutrons.
And those extra neutrons, they can go on to cause more fissions.
Exactly. That's the chain reaction. One fission triggers more, which trigger more. If you have enough fissionable material packed together, what's called the critical mass, the reaction becomes self-sustaining.
Below critical mass, it just dies out.
Right, that's subcritical.
Right.
Above critical mass, supercritical, the reaction escalates incredibly rapidly. That's the principle behind an atomic bomb.
Which historically changed everything. The Manhattan Project, figures like Fermi, Hahn, Meitner, Szilard, Einstein, culminating in Hiroshima and Nagasaki, a sobering part of this science.
Absolutely. It ushered in the nuclear age with all its complexities and danger.
But fission can also be controlled, right?
Yeah.
For nuclear power.
Yes, thankfully. Nuclear power plants use controlled fission to generate electricity. They make up a significant chunk of global power, about 15% currently.
How do they keep that chain reaction from running away?
Through careful engineering. A reactor core typically has fuel elements, usually uranium oxide pellets enriched in U-235. Then you have control rods made of materials like boron or cadmium that are really good at absorbing neutrons. By inserting or withdrawing these rods, operators can control the rate of fission.
What else is in there?
You need a moderator. Fission releases fast neutrons, but U-235 is much better at capturing slow neutrons. So a moderator, often just ordinary water or sometimes graphite, is used to slow the neutrons down efficiently. And finally, a coolant, again often water, circulates through the core to carry away the immense heat generated by fission, which is then used to make steam and turn turbines.
Like in a pressurized water reactor, the common type.
Exactly. PWRs use water as both moderator and coolant in a high-pressure loop. Safety is paramount, with multiple redundant systems and massive reinforced concrete containment structures.
But accidents can still happen, like Fukushima,
Okay.
often related to cooling failures.
Yes, maintaining cooling is absolutely critical. If cooling is lost, the core can overheat and melt, releasing dangerous radioactive materials. That's the major safety concern.
And then there's the waste. What happens to the used fuel?
That's the other big challenge, nuclear waste. The spent fuel rods are intensely radioactive, containing fission products like strontium-90 and cesium-137, some with half-lives of decades, plus leftover uranium and plutonium, which can have half-lives of thousands or even millions of years.
So what do we do with it?
Currently, most spent fuel is stored temporarily in pools of water at the reactor sites to cool down. The long-term plan in most countries involves sealing it in robust containers and burying it deep underground in stable geological formations. But finding suitable sites and ensuring long-term safety is, well, it's a massive technical and political challenge. Very controversial.
Despite the waste issue, nuclear power is getting another look because of climate change, isn't it?
It is. Because it doesn't produce greenhouse gases during operation, it's seen by some as a necessary part of decarbonizing the energy sector, even with the challenges.
Okay, so that's fission. What about the other side of the binding energy curve in nuclear fusion? The power of the stars.
Fusion is combining light nuclei, like isotopes of hydrogen, deuterium and tritium, to form a heavier nucleus, like helium. This releases even more energy per unit mass than fission. It's the process that powers the sun and all stars.
What are the advantages of fusion for power on Earth?
Potentially huge. The fuel deuterium from seawater, tritium bred from lithium is incredibly abundant. And the main product, helium, isn't radioactive. Fewer long-lived waste problems compared to fission.
Sounds perfect. So what's the holdup? Why don't we have fusion reactors yet?
But the sheer difficulty of making it happen. You have to force positively charged nuclei to fuse, which means overcoming their immense electrostatic repulsion. To do that, you need incredibly high temperatures. We're talking tens or even hundreds of millions of degrees Celsius, hotter than the sun's core, and high pressures or densities.
How do you even contain something like that?
You can't use physical walls. Researchers are primarily using powerful magnetic fields to confine the superheated ionized gas called a plasma. Devices like tokamaks are designed for this magnetic confinement. But achieving ignition, getting more energy out than you put in to heat and confine the plasma, sustainably, that's the grand challenge. We're getting closer, but it's still likely decades away for commercial power.
So fusion is not just an energy source. It's literally how the elements heavier than hydrogen and helium were made.
Absolutely. The Big Bang produced mostly hydrogen and helium, maybe a tiny bit of lithium. Everything else was forged inside stars through fusion.
How does that work?
Stars start by fusing hydrogen into helium, hydrogen burning. When they run out of hydrogen in their core, more massive stars start fusing helium into carbon and oxygen, helium burning. Even heavier stars go through further stages, fusing carbon, oxygen, neon, etc., creating elements up to iron and nickel.
But you said iron is the peak of stability. So what about gold, lead, uranium, all the heavier stuff?
Those elements heavier than iron can't be made by standard fusion in stars because it would consume energy, not release it. They are formed primarily during the incredibly energetic, chaotic events of supernova explosions, the death throes of massive stars. Those explosions provide the energy and neutron flux needed to build up the heaviest elements.
So literally the gold in a ring or the uranium in a reactor was forged in an exploding star billions of years ago.
Kind of mind-blowing, isn't it? We are, in a very real sense, stardust.
Truly profound. Okay, let's shift focus slightly to radiation itself and how it affects us. Living things, we're exposed all the time.
Constantly. There's background radiation from natural sources, cosmic rays showering down from space, radioactive elements like uranium and thorium in rocks and soil, which produce radon gas that can seep into homes. And then there are artificial sources, medical x-rays, nuclear medicine procedures, even tiny amounts in some consumer products.
What's the key difference between, say, radio waves and the gamma rays we've been talking about? Is it just energy?
Pretty much. The crucial distinction is ionizing versus non-ionizing radiation. Ionizing radiation alpha, beta, gamma, X-rays, high-energy UV has enough energy per particle or photon to knock electrons right out of atoms and molecules it hits, especially water molecules in our bodies.
And that's bad, creating ions.
Yes, because it creates highly reactive species called free radicals, particularly the hydroxyl radical, #OH, from water. These radicals are like chemical vandals. They can damage vital biomolecules like DNA, proteins, and cell membranes, messing up normal cell function. Non-ionizing radiation, like radio waves or visible visible light just doesn't have enough energy per photon to do that direct ionization damage.
So what determines how much damage ionizing radiation does?
Several things: the total amount of energy deposited, the dose, the type of radiation, its energy, and how easily it penetrates, how long the exposure lasts, and where the source is relative to the body.
You mentioned alpha particles are bad inside the body.
Extremely bad if inhaled or ingested. Alpha particles don't travel far, but they deposit all their energy very densely, causing intense local damage. Outside the body, they can't even penetrate the dead layer of skin. Gamma rays, on the other hand, are highly penetrating, so they're a hazard even from a source outside the body. Beta particles are intermediate.
What are the biological effects? What parts of the body are most sensitive?
Tissues with rapidly dividing cells are generally most vulnerable: bone marrow, where blood cells are made, the lining of the intestines, developing fetuses. The main long-term concern from chronic or high-dose exposure is an increased risk of cancer. Radiation damage can disrupt the genes that control cell growth, potentially leading to uncontrolled reproduction years or decades later.
Is there a safe level of radiation?
That's a very debated topic. While high doses are clearly harmful, the effects of low doses are harder to pin down. Many regulatory bodies and scientists follow the cautious principle that any dose of ionizing radiation carries some risk, however small. The assumption is often linear no threshold, meaning the risk decreases with the dose but never quite reaches zero.
So how do we measure radiation dose in a way that reflects this biological risk?
There are a few units. The gray, RIJ, measures the absorbed dose, the amount of energy deposited per kilogram of tissue. An older unit is the rad, 1 GI equals 100 rad.
But you said different types of radiation cause different amounts of damage for the same energy deposited.
Correct. That's where the relative biological effectiveness, RBE, comes in. It's a factor that compares the damage potential of a specific type of radiation to gamma rays or X-rays, which have an RBE of 1. Alpha particles might have an RBE of 10 or 20, meaning they're 10 or 20 times more damaging per gray.
So you combine the absorbed dose and the RBE.
Yes, to get the effective dose, which reflects the overall biological harm. The unit is the sievert, SV, gray X RBE. The older unit is the rem, rad X RBE, where 1 SV equals 100 rem.
Can you give some context for sieverts?
Sure. A typical dental X-ray might give you about 0.0005 millisievert, 5 microsieverts. The average person receives about 3.6 millisieverts per year from natural background radiation. Occupational dose limits are usually around 20-50 millisieverts per year. High doses causing radiation sickness start in the hundreds of millisieverts, or full sieverts.
It's quite paradoxical, then, that radiation, which can cause cancer, is also used to treat it in radiation therapy.
It is a paradox, isn't it? But it works because cancer cells are typically dividing much more rapidly than most normal cells, and rapidly dividing cells are more sensitive to radiation damage. The goal is to deliver a lethal dose to the tumor while minimizing damage to surrounding healthy tissues.
How's that done?
Often using high-energy X-rays or gamma rays from sources like cobalt-60, precisely aimed at the tumor from multiple angles. Sometimes radioactive sources like tiny seeds of iridium-192 or iodine-125 are implanted directly into or near the tumor. Isotopes are often chosen to have relatively short half-lives to deliver the dose quickly.
But there are still side effects.
Oh, yes. Because it's hard to completely avoid hitting healthy cells nearby, patients often experience side effects like fatigue, skin irritation, nausea, hair loss, depending on the area being treated.
Are there newer, maybe more targeted approaches being developed?
Definitely. One really exciting area is neutron capture therapy. The idea is to get a non-radioactive isotope, like boron-10, to selectively accumulate in tumor cells. Then you irradiate the area with low-energy neutrons.
And the neutrons react only with the boron.
Exactly. The boron-10 captures a neutron and immediately undergoes fission, releasing highly damaging but very short-range alpha particles right inside the cancer cell. It kills the tumor cell from within, with potentially much less damage to adjacent healthy cells. It's like a tiny targeted nuclear bomb going off only where you want it. A potential silver bullet, if it could be perfected.
So what does this all mean? We've gone from the heart of stars to the inside of our own cells today. It's quite a journey.
It really is. Nuclear chemistry touches on the origins of matter, the dating of history, powerful energy sources, cutting-edge medicine, and fundamental questions about risk and safety.
From the immense creative power that forged the elements to the destructive force unleashed in bombs, and the controlled power in reactors. It's a science of profound dualities.
A science that demands both incredible ingenuity and immense responsibility from us. It forces us to grapple with some of the biggest questions about the universe and our place in it.
We hope this deep dive into nuclear chemistry has given you a shortcut to being well-informed with plenty of surprising facts and aha moments to ponder.
Thank you for joining us on the deep dive, and a warm thank you from the Last Minute Lecture team for diving in with us today.